So going back to yesterday, we ended with this concept that we can have these small chemical reactions take place where we have double bonds or triple bonds that get treated with platinum usually and hydrogen to saturate them again. And so if we look at any number of these, we're going to see the same kind of application taking place. This hydrogen is going to insert itself over this bond. And so the net result would be a resaturation of that chain. And so we had initially two butene here. And now we just have butane. We went from this unsaturated alkene to this saturated alkane now. And the same thing, we see this platinum catalyst with hydrogen. We're talking about a hydrogenation reaction. That double bond is gonna go away. So we had cyclopentene here. And now it's just cyclopentane. So those were hydrogenation reactions. Hydrogenation reactions specifically talk about going to this idea of taking an unsaturated hydrocarbon and saturating it, turning the alkene or the alkyne back into an alkane. Hydration reactions follow the same kind of principle. The only difference is instead of hydrogen on both sides of the bond, we're going to have hydrogen on one side and hydroxyl, OH, on the other. But the application is going to be very similar. Hydrogen on one carbon, hydroxyl group on the other one. Now there is an order to things here. If the two carbons are different from each other. The hydroxyl group, that OH group, is going to go on the more interior carbon, the one that has fewer hydrogens on it. And the hydrogen will go on the more exterior. So basically the way to think about this is they're going to go toward their own kind. Hydrogen is going to go to the side that has more hydrogens. The hydroxyl group is going to go to the side that has the fewer hydrogens. Now in the examples that were given here, there's no preference. And the reason there's no preference here is because we aren't shown what the character is on those two carbons in terms of how many hydrogens each of them have. And in the case of ethene here, both carbons have two hydrogens, so either one's possible. This version of ethanol or this version of ethanol would be exactly the same. They're just redrawings of the same molecule. The other thing that we should notice here is that the reaction itself is different. Instead of catalysis with a inert metal like platinum or palladium, strong acids get used here. Most common strong acid of choice is sulfuric acid. So in these two scenarios, we're doing the same thing that we just talked about. We're doing an addition of water across that double bond. Now, in this first case, our double bond is right here. Both of the carbons are exactly the same. They both have just one hydrogen. So the placement of the hydroxyl group and the hydrogen doesn't really matter. Having it on the second carbon versus having it on the third. It's an ambiguous choice in this case. Because again, going back to our rules here, the hydrogen goes on the carbon with more hydrogen atoms. They both have the same hydrogen atoms. Here we definitely have a difference. There are more hydrogens on this CH2 group than on the CH group. So the H is going to go to the side with the more hydrogens. The OH is going to go to the other side. So it's CH3, CH2, CH, OH, CH2, H. This is what we would consider, and you see this sometimes in the homework sets. This is what we call the major product. So the major product is the one that we would expect based upon this kind of rule. That's not to say that the other one doesn't happen, but it would happen to a much lesser extent. Like,
why on like the
you could have done it either way. You could have done it either way. So if I wanted to kind of stay consistent here, yeah, either one would be fine. And so it really comes down to, I mean, you know, if you even want to get more technical about it, you know, this one here, the CH with the H hanging off of it, you could have rewritten as CH2. Other questions? Okay, the last bit here in chapter 11, concerns something called an aromatic compound. Now, aromatic compounds in general refer to a trait of alternating double bonds. But for the most part, when we talk about aromatic compounds in organic chemistry, we're usually talking about this structure right here. This structure right here is benzene. It has a chemical formula C6H6. And what we can see is unique about benzene is it's a ring structure and it alternates double bonds and single bonds all the way around the ring. What's even more interesting about benzene is that if we look at it from that kind of structural standpoint, here's the skeletal structure. We can very easily see that that double bond is just as likely to be in the opposite positions as where I drew it before. And so because of that, we actually think of that double bond as being able to move around the ring. You will see benzene often abbreviated as this six-sided ring with a hole in the middle. And that hole in the middle represents that double bond moving around the ring. So any of those three drawings for benzene is completely acceptable for benzene. So what do we know? Benzene is aromatic. It's a six-membered carbon ring. In terms of its structure is actually flat. It's planar. All of those atoms that make it up all fit in a two-dimensional plane of sorts, which makes for some really interesting kinds of chemical properties. And as I mentioned before, this way of showing benzene as this structure on the left versus this structure on the right, the two structures are completely equivalent. We can either show it then as this structure with a hole in the middle, if we're looking at a kind of a structural formula like this, or in the skeleton, just that cyclohexane with a hole in the middle. Now, because benzene rings are extremely common, they have a number of derivatives that are also common as well. So the three most common derivatives of benzene are these three. Methylbenzene, that is benzene with a methyl group on top, is sometimes referred to as toluene. Benzene with a nitrogen group on it. This NH2 group, which we haven't talked about yet fully, we'll get to. This is an amino group. So aminobenzene would be kind of the proper name of it. Aniline is the more common variety for it. Hydroxybenzene, benzene ring with an OH group on it, is most commonly known as phenol. Like we saw with the membered rings in the past couple of days, if there is only one substituent, we don't number the substituent since that would be assumed to be one anyway. When we get into multiple substituents, then it just follows kind of the rules that we've already established in terms of numbering. We number around the ring. We make a determination of numbers based upon kind of giving us the lowest combination of numbers possible. So on the left here, you have chlorobenzene. Chlorobenzene is kind of just your factory run-of-the-mill single chlorine on a benzene ring. Don't need to put a number to it because, again, one is assumed if it's the only one there. Stick on a second one, and now we have to number them. If they're next to each other, it's 1, 2. If they are completely opposite each other, it's 1, 4. If they're kind of in between, then it's 1, 3. But we always would name one of them with 1, since that would obviously give us the lowest combination.
Doesn't matter which double bond. They're all at the top.
Keep in mind, these could be in any position whatsoever. So what we're calling 1,2-dichlorobenzene here, if I drew it this way, it's still 1,2-dichlorobenzene, because we would just start our numbering from here going around instead of at the top. So it's just like that for any ring structure. We start numbering the ring wherever we find that first substituent. And then we either number it clockwise or counterclockwise based upon where the other groupings are. Again, the whole idea, lowest combination of numbers possible. All right, so going back through this, what is the correct name for compound number 1 here? Okay, we can take A off of the list. This isn't a hexane, we've got a benzene ring here. So it's either B or C. The reason we come up with B is because since there's only one group on there, the 1 is implied, we don't need to state it. For our second one here, we have dimethylbenzene listed out here, and that's common for all 3 of them. It's just a matter of which position is it. Now, again, it doesn't matter where I start numbering. I just need to start numbering at one of those methyl positions. So let's just, for the sake of argument, start here in this side position. I have the options of, in red, going clockwise, I would end up with 1,5-dimethyl. Or if I go here in blue, numbering counterclock, I would have 1,3. The 1,3 is the lower combination of numbers. That's the one that's going to be correct. But they're both dimethylbenzenes because, again, I've got 2 methyl groups on this ring. It's just a matter of the position and numbering the position appropriately to give us the smallest combination of numbers possible. All right, questions? Okay, so that is the end of chapter 11. Now, I'll recognize chapter 11 was a lot to swallow. There's a lot going on in that particular chapter, which is why it's kind of, we've been dragging our feet through this, taking a little bit longer than the standard week to do it. And that's completely okay, because we needed to use that time. And that's why I'm giving you the extra time at the end of this week, just to kind of start to make some sense out of it. The good news is that this does all build. And so what we get into next, getting into chapter 12, is just building on this foundation that we're establishing in chapter 11.